Okay, thank you very much for the introduction a couple of hours ago. So I am going to present basically one method with a few variants that we have been developing in the last few years in my group to deal with small data. So whenever you have a few data points and you want still to get some predictive model. So I typically start with the Venn diagram of the whole artificial intelligence zoo, but I want to pinpoint one particular subset of machine learning that we are really interested in. Back to representation learning. So the idea is that a neural network can be interpreted as a set of transformation, linear and nonlinear transformations, and each result of each transformation is a representation. And so people typically are happy to look into the representation inside the neural network in order to try and understand what the neural network is understanding about the input data. And there is a more direct way to do representation learning. This is symbolic inference. That is basically what I will do now. And just to get out of the jargon, so inference means just learning from data. And symbolic means that the outcome of the learning is an analytic equation. Of course, it's always an analytic equation, but here we are trying to learn more or less like human would do by looking at data and try to look into regularities. I will show examples so you will see what I mean. And then we have, as a subset of this symbolic inference, we have regression, classification, and also some more exoteric descriptive rule learning that I will not touch today, even though we are active also on that side. So the general idea is to learn representation that are low dimensional. We are very happy if they are 2 dimensional because we can put them on a slide. But of course, if they have to be more than 2 dimensional, why not? But the idea is that, okay, let's say just with this the very first application of this methodology to learn map for octet binaries, you want to find a way. It's getting worse. You want to find ways to represent all the possible octet binaries in a 2-dimensional plane, and the catch is to find the axis in such a way that you can still look into them and understand what's going on, such that you have all the zinc blende forming on one side and all the rock salt forming on the other side, and if you have more crystal structures, as you do, you can allocate also them in kind of regions. And in this case, maps is more thinking at cartographic maps, like Europe or the rest of the world. And then you could have map for other properties. Or you could have also continuous map in which you say, okay, if I'm looking at the absorption of some molecule on a surface, I could have the Goldilocks zone in which the absorption is favorable for catalytic behavior, and so you also have a kind of region where you want to land and have a prediction on which kind of external condition you have to generate in order to get the right conditions. So the methodology combines so this idea of symbolic regression, so learning equation in this way. So we start by producing basis functions that are nonlinear, function of some input variables. So what are the features in every machine learning? You start combining the features with a kind of vocabulary of nonlinear operators, could be also linear, as a subset. And then you write an expansion over this basis set. This is always a very nice idea if the basis, if the expansion converges. The catch is that you want to have this expansion as short as possible. And this is where the compressed sensing idea comes in. That is a technique from signal analysis that tries to find the few basis functions that would describe your data as accurately as possible. Mathematically, you write something that is well, a cost function. You want to minimize an error, but then you penalize every time you switch on one coefficient in that expansion there. And this is mathematically written as norm 0 of the coefficient vector. And if you're a graphic person, what the method is doing is picking up columns in this sensing matrix. So basically, you're trying to express linearly a property is a linear expansion of a basis function. The basis functions are represented as columns, and you just pick up columns in that matrix. Let me skip Lasso. The way we generate the basis function is by combining a dictionary of operators. This is just an example, not necessarily what we do in practice. And then you say, okay, I possibly sum quantities of the same unit, of the same physical dimension, and then we operate and get a more complex expression like this one that you see here. So a property is a difference of some energy divided by the sum of some lengths. And then this is done iteratively. So this leads me to the fact that I want to skip more details on the methods. And if you want to know or learn all the details, you just go to the Nomad AI toolkit. And one of the notebooks that are in the toolkit, one of the very curated notebooks that we have let you go through step by step the methodology that is called SISO, Sure and Independent Screening and Sparsifying Operator. That is what we are using. I'm explaining now, and I go directly to the results. So one of the first applications was to find an improved figure of merit for or tolerance factor for predicting whether materials with the general ADX3 formula would crystallize or not as perovskites. It's getting a bit old, but it's cited amongously, I would say. I think because we end up with a machine learning model that looks like this. So you can forget about the machine learning. You get an expression that you can plug in. Every person working, or many persons working with the perovskite will have this Shannon radii tabulated for all the atoms. Don't go into detail what they are. Something related to the size of the atoms in the crystal. But it's a tabulated thing, and then you need this oxidation state, and you get it with a very simple model. And with the price of complicating a little bit the human learned factor from Goldschmidt back in, say, 100 years ago, we get a much better accuracy, but we also get a probability prediction that is monotonic. So basically we can say that materials that land in a certain region will have a certain probability to be perovskite, to crystallize as perovskite or not. And outside that, we have 100% probability that they are or not perovskites. And then you get the maps that I was hinting at the beginning, basically as a function of this radii, that basically is just the composition here. You fix say that X, the anion is the oxygen, and you transverse this two-dimensional map. You can have four-dimensional map because essentially you have 4 dimensions here. And then you see which material would be classified as perovskite or not. So also here we have a notebook that shows how you get to this particular result from our data set. And if you have a different data set or a large data set, you can retrain and see if you can do better, and you get the results on the same graphic as in the paper, because we use exactly the same library. So this is just to show that the method is successful. And a word about the complexity. So I said that we have this expansion over basis functions, and you want to probably know where to stop this expansion. And it turns out that with good old cross-validation, you can find, again, the sweet point where you do not improve very much. So this would be the prediction error as a function of, let's say, complexity. And then you say, OK, I stop at some point when my prediction error doesn't improve when I increase the complexity. This is what you do every time in machine learning. Here, the complexity is particularly transparent because it's the number of basis functions that you select. And how complex each basis function is nonlinearly when you build it. We don't have a good definition of complexity for nonlinear function, and we are working on that. I mean, not only me, but yeah. this is related also to this point, so that you want to have the most simple expression with the data that you have at hand. That is again Occam razor, this time the real one, not what people always miscite, basically. So as complex as it has to be. Now, let me go quickly to the kind of updates or improvement of the method. One is a multitask learning variant, where we say, okay, let us learn these expansions for different properties. So we learn different properties, and we impose that the descriptor is that is selected is always the same. So the basis set as function is always the same. What changes are the coefficients for each different properties. So essentially, again, if you see better with graphical representation, it would be solving n different linear system where you pick up always the same columns, but the learning coefficient would be different. One advantage that you have is that, okay, if the properties are related on a conceptual level, it is better to have the same descriptor and then just a linear relationship. This is what you would have at the end of a neural network at the end, by the way. And the other thing is that you can deal smoothly with missing data, because you don't have to have all the properties tabulated in your databases for all the data point. The blank spaces are just not dealt by the solver, and we train with the incredibly sparse data set where you have data all around the metrics, and still you get some robust predictions. So the point would be, what would be properties that are related to each other? Well, one nice example would be that the coefficient on the expansion, so the descriptor is selected by the method. The expansion coefficient will be different for each property, but it could be that there is a parameter that changes smoothly between one property and the other. For example, you're measuring the same property at different temperatures or at different frequencies, right? And the next is the application when we were looking into some properties of catalysts containing vanadium. This was a purely experimental data set in which we wanted, this is just to scare people that chemical equation is actually, I don't know why the arrows got, this should be a double arrow, I don't know what happened there. So we were interested in this acrylic acid synthesis, and we had a very curated data set with 9 materials, but each of them at different temperatures. So we could exploit the idea of this multitask learning as the same property as different temperature. This is what I show would be the example of the selectivity for this particular set of materials. And we had the order of 50 different features that we gave to the algorithm and asked you to select which one were the most important and give to predict selectivity of the material as a function of temperature and give us a predictive rule. So the crosses would be the prediction that are quite good. And also we have the coefficients have a certain variability with respect to temperature. And therefore one can also fit as a function of temperature and have a kind of smooth representation like this one that says, okay, we collapse into one dimension the descriptor, so this is the material and this is the temperature, and you get this nice plot that is not anymore linear because it captures nonlinear correlations, and then you would have that some certain material would have a selectivity that changes as a function temperature. In particular, this one would be the one that has more variability with respect to temperature. And what do you do at this point? So what do you learn from this kind of learning is that you get, so this would be the descriptor that contains features at different level of scale of describing your material. So something related to the mesoscale, something related to the electronic, so the work function to the electronic features of the material. the surface, most importantly. And the idea is that if you can tweak these features on your material, you could get a better material. For example, you can prepare it in a different way and change the pore fraction and increase its selectivity. Therefore, so the darker, the higher the selectivity. So that would be a welcome thing. So you analyze the descriptor and you kind of come up with the ideas on how to modify your material. So this is where we get to material design. Very quickly, the method has been having a lot of development in the last few years. So first of all, we have a nice C++ code. And then now we have a very kind of laid down grammatical rules when you form this nonlinear function. So you only sum homogeneous units, and then you have always unitless arguments in transcendental functions. So you take care that they're always unitless, and then a few other things. Very important that we added a nonlinear parameters in these nonlinear functions, that they are relaxed in a kind of greedy way. If you are interested, ask. Also, we have multiple residuals. That was a kind of stiffness that we had in the original formulation. So the method has become much more efficient, and in particular with the very recent. So the paper is submitted, but you can already use it. The GPU porting that has an overall speed up of 10 times. Okay, I want to go to another application because I want to show another very promising implication of this kind of algorithms, right? So most of the time, I must say, as I'm reviewing, I don't know how many papers per month with machine learning, people are content to show that they have fitted their training data essentially, or maybe they can say something about the test data, but what something is useful for besides saying, oh, okay, we have a model that probably works, is sometimes unclear. So this is one idea, and how you can use simple models like the one that we produced. So let's say we were interested in the thermal conductivity, lattice thermal conductivity in particular of a set of materials. We get a good prediction, and we get an expression that some may say is not particularly simple, but it depends on only a few parameters. So most notably, should have, okay, yes. Yeah, there is a comparison with the literature, not important at this point, I would say. So we have parameters that depend on the molar volume. So you have the material, you have to optimize it, and you have your molar volume. Say you do it with DFT. And then you have something that depends on the Debye temperature. So you say, okay, I have now optimized my material. I calculate harmonic frequencies, phonons, and then I have my Debye temperature, a model for the Debye temperature. And then I have something that is an anharmonic feature of the potential energy. So you need to do some molecular dynamics there. So these features have a kind of hierarchy in computational time that you would need to invest to get them for your material. And so let me go to the result, forget about the plots here. You can say, okay, if I'm looking for a material that has particularly low conductivity, for example, I look how the materials would appear with respect to these features. And I say, okay, I can define a threshold on molar volume, Debye temperature, and anharmonic coefficient in order to get to the material that I'm interested in. The catch is that before you start the analysis, maybe you can guess that these are important features, but you are pinpointed that these are the best statistical in order to do this screening. And also where to cut when you do the screening. So you have seen probably this screening funnel over and over in literature in the last few years. This is a way to get it sort of automatically from your data, even from relatively few data points. We are talking about few, so 200, between 100 and 200 data points. You typically get something meaningful. We have a notebook also for that one in the AI toolkit. So the last point is that, again, since you have analytic expression that you can manipulate with your basic calculus, you can say, okay, let's say that you have some complex properties. Complex property meaning that the expression that you need to distillate from your machine learning in order to predict the property from the feature is complex. In terms of neural network, you need many layers. In terms of symbolic regression, you need very nonlinear function, a combination of them. Now imagine that you have another set of properties that are much more simple to fit and give good prediction. You could use, so if the complex property depends on the simple ones, you can kind of chain the learning. And I show you an example so that I can get out of the symbols that I'm normally too much into. The idea is that, again, pair of skies, since we had the data and we were predicting, I think it's the bulk modulus, yes, bulk modulus. And we have a model where we use as features to predict the bulk modulus the lattice constant and the formation enthalpy from DFT calculation. So you need to know the material. In the database, you have the lattice constant and the formation energy. And with that one, you have a very nice prediction of the bulk modulus, much better than if you don't use this property because you say, I don't want to use DFT calculated properties. But now, if I learn the lattice constant and the enthalpy from basic quantities where I do not need to do the DFT calculation, I get essentially the same prediction if I change the model. So I substitute model for lattice constant into my model. And I don't have an explanation why the errors do not propagate, do not explode, but they always kind of tend to be, because maybe something physical behind is captured by all the models, so they do not sum up. I mean, I don't know if this is always true, not necessarily for sure. And then I want to just give a glimpse on a very recent application that I've been doing in Erlangen, where we have experimental data on a class of these bulk heterojunction organic absorbers, so solar cell, organic photovoltaics, that are printed on a substrate, and in group of Professor Brabeck, Christoph Brabeck, who is also a FAIRmat PI. They have a robotic lab, so they can go over batches of different simulation where they change the concentration of these chemicals and few other parameters that they are summarized in this part here. So yeah, something from the productions, rotational speed of the spin coater, how much of each of the donor and acceptor you have in your production, and we have data points that go from this process parameter to the performance. So for these photovoltaics, you have the power conversion efficiency, the open circuit voltage. So if you are into the business, you know that these four numbers are those that people always look into. And we can learn them, even if we have few tens data points, let's say. Then we have also a physical model called drift diffusion model. It tries to understand what important physical parameters of the chemicals that you have in your photovoltaics determine the performance. So when you do the experiment, you can control the process and measure the performance. From the modeling, you can control some parameters in your model and get the performance. How do you link these two things? You learn them both and you chain them, invert whenever you need to invert your expression and so on. So we can go from process to drift diffusion model and vice versa with very little cost. And the question is, does it work? Well, that is what we are doing. So for some properties, it works, meaning, so what I'm showing here is that we are predicting one of these properties from the process by this kind of chaining, and you get a very smooth prediction. In other cases, your prediction is very bad. these are still positive signals. It means that there is not enough information in your features in order to do that learning. Or it is a good indication. Of course, you cannot exclude that you just didn't get the right model. But whenever you get this cloud of points, you start suspecting that your expression is not invertible, it's not learnable from the data that you have. So you go back and see if you can do something. But when you get the prediction, so we have now running some experiments in which we were kind of trying to improve some of the parameters. This is still an open story, so you don't know, but with how accurate are certain prediction, it is interesting. As a side point, we don't have any validation. So when we train, we don't know how this is the connection between the process and the diffusion model. So because this is completely unknown by the data set. So this is what we have to prove. And this is what we are doing now with the robotic lab. Okay, I think I can stop here. Yes, the next topic is for after the break, if you're interested. This is the people that I have to acknowledge for all this work, and I thank you for your attention. And finally,
thank you, Luca. Questions?